Okay. Last week we have discussed about this process control, this process diagram related to the operating systems. Basically, how a schedule, right? How a schedule is executed. Basically, it's in ready, running, and block status. So those are the three status that the schedules. So any process is like going through these processes. And here actually, so some of these steps executed in the processor side, and some of the status are there in the memory side, right? So we need to know about that as well, which are in the memory side and which are in the processor side. So let me show that again using this process management, and you need to know about memory and processor. So this was really considered with the memory and processor side, but still, so this part is so a little bit important. So process management, I need the diagram part. Okay, so just think about this part, and yeah, none of the diagrams explain that properly, but anyway, let's go to this today. So this was another diagram, so that like they can ask one of these diagrams, right? Right, they can ask one of these diagrams in the examination. Here, see this new process. Basically, this side is, you can see this side is memory, and this side is also memory, but it's not indicated properly here. When a new process it comes from the memory. It's main memory basically, right? Entry level, the process enters into the processor from the memory side. From memory, it comes as a new process, and then the process will be ready state, right? When the process comes to the processor, is in the ready state. Initially, it will not start running, but the ready process gradually with the scheduler dispatch means every process has a time. So every process will get sometimes, so there are different mechanisms like round robin algorithm. Round robin algorithm is a fair algorithm. Fair algorithm means like everyone will get a chance. So it's like, so let's say 4 processes are in the cycle. So let's say these are the processes. The process 1, I'm going to draw here. Process 1, 2, and process 2. And sorry, process 1, process 2, process 3, and process 4. There are 4 processes. 4 hours explain that, and each process will get. So first, let's say first running is first will come the process 1. Second is process 2. Third, it is process 3, and fourth is it is process 4. Again, it will come to the 1. First process, second, third, fourth. Again, it will come to the 1. This is called round robin. Round robin, right? Round robin algorithm. So based on the algorithm it uses. So this is normally, so round robin algorithm is there, but mostly there is something called priority scheduling. Why? Because some processes need high priority. So some processes need to execute very soon. For an example, think like that you got a virus infection, then the antivirus should be given the priority to stop that. So likewise, so priority based scheduling is more common. So round robin is there, yes. For equal priority processes, it's possible to execute round robin. If those are equal priority, samana priority round robin common, each one will get similar chance. So that is okay. But the other one is, so if priority scheduling is special when you need, like operating system is given high priority, and sometimes even the virus and or virus scanning process can be given high priority. So priority is also there. Then when a running new process come to the ready state, then with the scheduled dispatch, it is going to the running state. This is number 1, and this is number 2. And after running, so interrupt. So what is interrupt? What is interrupt? Interrupt. Any idea about interrupt?
Disturbance to the process.
Yeah, it is disturbance to the current process. Any kind of, it's kind of, so you cannot say disturbance, but the, yeah, that is also okay, but the mainly it's kind of interrupts are required, right? So we will think interrupt should not happen. No, interrupts are required. So for an example, think that I'm doing this lesson and somebody is shouting here and somebody is shouting. I have to mute my microphone to attend that, because that is interrupt. My normal process is doing the class. If somebody come and talk to me, I have to mute my microphone and attend that. So similar to that, when you run this, so let's say suddenly a virus came, that is interrupt. When you run this, maybe automatic, that is called preemptive, automatic termination. Because the current time given for the task one is over. So it can be again going to the ready state because of the timeout. Timeout is also interrupt. Or interrupt can be, okay, let's say there is a, let's say, something like this. Okay. Screen saver. Screen saver is in the string. Screen saver, a screen play with it. Let's say screen saver is in the string. And suddenly you press when screensaver is in the string, suddenly you press a key. Then the screensaver will be interrupted and it will be terminated. So basically, so it can be even terminated and it can be again going back to the ready state. Basically, the screensaver is going to ready state. Again with the schedule, maybe if you are idle, again it will start running. When someone press the key, again interrupt, it will ready. And after some time, again start running. So this is like screen lock in your mobile phone. Think about screen lock. Screen lock, you unlock it. You unlock your mobile phone and keep it for a while. So let's assume you cannot, right? Let's assume you cannot pay attention to this. Right? Let's say you cannot pay attention to this. So maybe for some time you keep your mobile away. Then what will happen? So it will be automatically locking your screen. Right? It is automatically locking your screen. Right? So that is again, when you unlock again, so again the screen is running, but after some time it's again locked. So likewise, so this process is going from running to ready and ready to run. Okay, in case so termination happen when the process is exit, terminated process won't come to the running state again. It need to start as a new process and come back. Terminate to never run when a new process and the waiting state. So let's say there is an IO event. IO event means input output event. Okay, for an example, so you want to delete a file. So it prompt a message and asking, are you sure you want to delete the file? You want to delete the file. When I try to delete the file, it's asking, are you sure you want to delete the file? Until I select yes or no, it remain in the waiting stage. Right? Until I press yes or no, it is waiting in the it's there in the waiting stage, because it cannot decide what to do, whether to stop or whether to run. So if I am not going to confirm that, it will be there forever, because no timeouts will come, right? So let's say I want to close Excel sheet. I want to close this Excel sheet. I'm going to right click and close this. Okay, if there are changes, if there are no changes, it will close. So let's say if there are no changes, so it's closing. And let's do the same for the operating system lesson. Just put in some character, garbage character. Then I'm trying to close this. It's asking, are you sure you want to close this? I'm not going to do anything. I'm not going to do anything. I'm going to deal with the existing this string. So without responding that. So that is IO wait. It's waiting for our input or output. Otherwise, it will remain as it is if I'm not going to give any input output. So that is the waiting stage. So this is more clear, I guess. So it's better if you can write down this for the process state diagram. So please write operating system process state diagram, operating system process state diagram, and draw this diagram, please. Operating system process state diagram. Next is about this. Cancel it. Right. Next important thing that will be checked in the examination is this MMU, the task of MMU, physical logical addressing. So what are these? Physical and logical addressing related to this MMU. So in the CPU, so CPU will first recognize the address as a logical address. Address is a memory location of anything. You can any maybe memory location of input device, output device. It can even be an instruction. So whatever the things, all are given memory addresses. So these memory addresses reside in the inside this MMU. Sorry, in the processor. In the processor, actually, there's a unit called MMU, memory management unit. So there is logical address. So if this logical address, first it will check is there in the page cache. So what is page cache? Page cache is basically, so when there is a large program in the hard disk, let's say 1 GB program, so it will be divided into manageable pages. Let's say there's a large book. So we cannot remember each and everything in the book. Each and every page we can't remember, but still we can turn one page and try to read and memorize that. So similar to that, when there is a large file, when there are a large set of instructions, the computer keep it in the storage and slowly fetching or slowly taken into, actually it is divided into pages, and these relevant pages are acquired and taken into the page pool. So that is called paging, right? So understand this concept. So these are very simple concepts, but the thing is, if you are not understanding this very well, then so you are in big trouble. So let's say this is the whole bunch of instruction. In paging, this instruction is divided to a pages. Pages means small chunks. So these chunks are called pages. I'll show this practically where these chunks are saved. There is something called page file. So let's say this is your program and it has some pages, as you can see here. So let's say you have another program or data, anything, right? You have another thing. I'm going to draw this in color. And that also has pages. Also has pages. So these are the pages in this. So these manageable chunks of the pages actually, so this is dividing is called paging. Dividing program into manageable chunks. All pages is called paging. Okay, so let's say this is your program 1 and the right side here, there's program 2. So what will happen? There is something called page file or the virtual memory. Let's say this is your virtual memory or page file. So that will acquire most relevant pages from, okay, let's say few pages from these and few pages from the other one. It will acquire most relevant and frequently used pages to this page, actually this virtual memory. So this is your virtual memory, or we can call page file, right? So first of all, when there is a logical address, it will check in this page-based memories. So if it is yours, then the page number and the relevant frame number. Page number and frame number means this is, if this is your page number, So let's say this is your page number, and relevant frame number is where this is reside. So let's say this is, and this is your frame number in that case. I hope you understand, right? So frame number is the physical location of that page. So there's a page in, so that is physical location of the frame is, okay, if it is not there, if it is not there, it's trying to search that in the page map table, right? Page map table means, so in between this physical memory, in this between this memory and the page pool, in between the memory and the page pool, there is a page map table. There is a page map table in between this. Page map table will also has the page here. You can see the page is, let's say 3, the frame is 10. Page 3, the relevant frame is 10. So then it will go to the frame, and then it will go to the physical address of the memory and read that. So this is how the frame acquiring is happening. Which part? So may I know? Yes, I can explain it again, but may I know which part you're asking?
Page number and frame number.
Yeah, page number, and this is actually, so the page cache is the closest location. Page caches will have most frequently accessed pages and frames. Page is basically, right? Page is basically the virtual memory location. Frame is the physical memory location of the particular data. Okay, if you want to locate something, basically the computer will have the logical address, which is the page-based memory. It will access your virtual memory, right? It will think, like, CPU will think the actual memory is your virtual memory, but it is not. The virtual memory has acquired these pages from the physical memory. Virtual memory has acquired the pages from the physical memory. So you need to locate the physical address. You need to locate the physical address. So therefore, when you know the page, you need to find the relevant frame. Then only you can access the data. Right? In the page cache, most frequently accessed pages and page numbers and frame numbers are there. So CPU can locate that from the page cache and easily access the relevant physical address and to bring this data. So if it is not there in the page cache, then it will search in the page map table or the page table. Page table will also have, it's also similar, page number and frame number. So mapping is happening there. So it can go to the relevant page number and find the frame number and then go and access the frame. Why this is there? So there is a reason, because you can't store the full memory address in an instruction. So let's say you have 4 GB memory. Let's say you have 4 GB memory. 4 GB memory. So let's say your memory has, this is byte addressable. The memory is byte addressable. Mean to each byte you have address. Byte addressable. It means to each, so ugly text, sorry, byte addressable. I'll show it, byte addressable. That means each byte will have an address. Each byte will have an address. Okay, now tell me how many addresses will be there. Okay, yes?
2 to the power 30 bytes.
Sorry?
2 to the power 40 bytes.
2 to the power 40. Is it? 4 GB means, okay, totally 4 GB, right? Totally your memory is 4 GB. Understand my question. 4 GB means, total memory is 4 GB, right? 4 GB means, let me write that in the in bytes today. Let me write that in bytes. 4 GB equal to 4 into 1 GB means 1024 GB can MB. So that into KB is 1024. Right, that into byte is again 1024. This number of bytes, agree?
Yes.
Right, first I have converted that 4 into, this is gigabyte, megabyte, then kilobyte, then bytes. With this number of bytes altogether, this is actually 2 to the power 10, no? 2 to the power 10. Isn't that so? This is also 2 to the power 10. And this is also 2 to the power 10. This is 2 to the power 2. Altogether, the value will be 10 plus 10 plus 10. 10 plus 10 plus, that is 30, 2 to the power 32. Okay, agree or not?
Yes.
2 to the power 32. So 2 to the power 32 bytes are there. So each byte has an address. Ek byte again address unique address. Each byte has this number of bytes, right? This number of bytes. So if each byte has 32, sorry, each byte has an address, how many bits you need to write such address? How many bits you need to write such address? Okay, so I'll make this question simple. But I'll make this question simple. So let's say you have 2 bytes in your memory. Only 2 bytes. 2 bytes, sorry, 2 bytes in your memory. Each byte has unique address. Then how many addresses? 2 addresses, right?
Yes.
Each byte has unique address. So address 1 is, maybe you can say 0 is one address, 1 is another address. 0 is another address, 1 is another address. So how many bits you need?
For one address?
No. To write 2 addresses, how many bits you need? Address has only 1 bit, right? 2.
Yes.
It has only 1 bit. Address has only 1 bit. Let's say your memory is 4 bytes. Your memory is 4 bytes. So I'm simplifying it. That means 2 to the power 2 bytes. Agree?
Yes.
So if your memory has 4 bytes, it's 2 to the power 2 bytes. So then you need 4 unique addresses. So you need 4 unique addresses. Then how many bits you need? So what are the unique addresses? 001 is one unique, 01 is another one, 10 is another one, and 11 is another. So you have 4 addresses. 1, 2, 3, 4 addresses. Okay. Agree or not?
Yes, sir.
So 1, 2, 3, 4 addresses. So how many bits you need? Each address will have
2 bits.
2 bits. Okay. Now come to the scenario. You have 2 to the power 32 bytes. 2 to the power 32 bytes. So you need to give unique addresses. Each address will have how many bits? Each address will contain
32.
32 bits. This can be asked in the examination, right? So this is general. So I'll not give any note on this, but this is very general thing. It's all about 2 to the power numbers. But this can be asked in the examination. The other way also it can be asked. So let's say your memory has 32 bits. Your memory has your memory address will have 32 bits. So what is the maximum capacity of random access memory you can install to this computer? If you have 32 bits, the maximum capacity of random access memory that you can install in your computer is other way, it is 4 GB. Understood? Right? It's only 4 GB, right? 32 bit address එකක් තිබ්බොත් උපරිම capacity එක memory එකේ 4 GB. 4 GB වලට වැඩි වුණොත් address ලියන්න පුළුවන්ද? Hello? Am I audible? Hello, am I audible? Can you hear me?
Yes, sir.
Okay. So tell me, so if 32 bits, what is the maximum capacity of memory? If 32 bits, what is the
4
max? Huh? 4 GB.
4.
4 GB. If your compute, if your RAM is more than 4 GB, can you write addresses using 32 bits?
Huh.
No, not enough. Why? Some places, some bytes will not have addresses. That is the thing. So this is for the byte addressable memory, right? Remember the case. This is byte addressable memory. There is another one. There is another one that is called word addressable memory. There's another one that is called word addressable memory. So byte addressable memory, each byte will have address. Word addressable. What is word? Word is the length of instruction that computer can take into the processor in one time, at one time. Length of the instruction or length of the stream, length of the instruction basically, which the computer can take into its processor. So this is what you call 32-bit processor, 64-bit processor. Have you learned something like that? Have you heard something like that? 32-bit processor can take 32 bits at once. 32 bits, right? 32-bit processors can take 32 bits at once. 64-bit processors can take 64 bits at once. Okay, 32-bit processors can take 32 bits. 64-bit processors can take. So this is called word, right? Word එක කියලා කියනවා. මේක පාර process එකට ගන්න පුළුවන් ප්‍රමාණය. In the word addressable memory, each word will have unique address. Let's say 00 is one word, and 01 is another word, 10 is another word, and 11 is another word. So if there are 2 bits in addresses in word addressable memory, what is the capacity of that memory? If there are 2 bits, 2-bit address. So listen carefully, right? If it is 2-bit address, how many unique addresses? If it is 2-bit address, how many unique addresses?
4 bytes. 4.
4 addresses. 4, not 4 bytes. It's 4 addresses, right? 2 bits both. 4 addresses. Okay. Agree?
Yes, sir.
Right. Okay. Now, what is the size of, or what is the capacity you can store in each address?
32.
32 bits. That means how many bytes?
4.
4 bytes. Right. Then what is the total capacity of the memory? You have 4 addresses. Each address will hold 4 bytes. So total capacity is 16 bytes. Agree?
Yes.
16. This is for word addressable memory, right? So understand carefully. Byte addressable memories will give addresses to each byte. Word addressable memory will give addresses to each word. Byte addressable. If it is byte addressable memory, so you have same words. Words, let's say you have similar kind of words, and word length is 32-bit. 32-bit words, but addresses will be something like this. Okay, let's say 00 is this address. The next address will be 0001, second address 1011. The next address will be 100, right? In binary. The next address will be 1000 in binary. The next address will be 1000. So what's going on? This is byte addressable. Why? Each byte has address. So hexa walin tama normally මේක ලියන්නේ. මේ binary වලින් ලියන්නෙත් නෑ. So normally you write in hexa. So let's say hexa 0. Hexa 0, 0 is the first address. The next address will be hexa 0, 4. The next address will be 0, 8 hexa. Next address will be 0C. Next address will be it's 1, 0. So next address will be 1, 4, 1, 8, 1C. So the next address will be 2, 0. This is in hexadecimal, right? It's going 4 by 4. Why? If it is byte, yeah, each byte will have address. So there are 4 bytes here. So 4 bytes will consume 4 addresses. Next 4 byte, that's why next address is this. But in word addressable, it's not like that. Hexavalently would make a, if I write this in hexa, so it should be 0, 0. So the next address will be, yes, 0, 1. Next will be 0, 2. Next will be 0, 3. Next will be 0, 4. Right? It's going smoothly. For each word you have address. Which has higher capacity, if it is byte addressable or if it is word addressable? Which can store more?
Word addressable.
Yes, word addressable. It will consume less address space and store more. It will consume less address space and store more. Byte addressable is very easy because each byte you have address. It's very easy to address. Here actually, so the consumption is very high because you can get data in this address, but let's say you stored part of the data here and another part of data here, then the second part cannot be accessed. Why? Because this has only one address. එතකොට මෙයාට තමයි එයාව තමයි access වෙන්නේ. මේ පැත්ත එක්කෙනාව access වෙන්නේ. ඒ හින්දා ඇත්තටම මේ ඊළඟ එක්කෙනාව මේ line එකට දාගන්න. So that will waste some storage. But byte addressable, it will space saving, right? Word addressable will waste the space. Byte addressable is space saving. Okay, so these are the memory types. There are 2 types of memories: byte addressable memories, word addressable memories. Anyway, so what is address? This is address, right? This is called the physical address. Physical address again. The logical address is address which is pointed to virtual memory. Address which is pointed to virtual memory is called logical address. Address which is in the main memory is called the physical address. I think this addressing thing is clear to you now. Is it?
Yes.
Okay. So now you have the word addressable, byte addressable, and what is happening, actually what is done by MMU is converting these logical addresses in the virtual memory to physical address in the main memory. So that is the task of MMU, physical manage, right? So remember that the main memory, the theoretical address range, right? Why? Because the memory can store, the memory addresses can be pointed to memory itself, and sometimes these memory addresses are pointed to devices. Therefore, so you can't utilize the entire address space for storing purpose. Some of these are devices. A address වලත් 100%ක්ම storage වලට පාවිච්චි කරන්න. Some are pointing to the devices. මොකද input output devices අඳුරගන්නේ ඔය address වලින්ම තමයි. එතකොට ඇයි මේ logical address එකක් ඕන වෙන්නේ? Because you know that address, if it is 32 bit length, address එකක් 32 bit දිග වුණා. 4GB RAM එකක address එකක් ගත්තොත් theoretical අපි ගත්තොත් 32 bit, instruction size එකක් 32 වුණා. So can you send the address and instruction all in one go? Understand this carefully. Let's say your memory address size is 32 bit. Let's say your instruction size is also 32 bit. Now, is it possible to send instruction?
No.
No. Why? Because the length instruction will consume 32 bits. The nature of instruction is basically instruction will be created this way. The first part of the instruction is what to do. The second part of the instruction is to which address is used. The next part, this is one type of instruction. The second type of instruction can be, first is what to do. Just throw in this, what to do. And the next is two memory addresses. This is another type of instruction. Two addresses. And there can be some instruction without any address, just saying what is the instruction, only the instruction. So not mentioning any address. Even there can be some instructions which has the instruction and three addresses. So these are instruction types. So different type. This is there in actually degree courses, but you don't have up to that much. You don't have. I'm just telling you instruction types. I'm just telling why this is actually needed. Okay. This is therefore BIT like examinations. Opcode is the basically what you have to do. And next you can see the register address, and immediate address. Opcode again is the what to do, and you can see some addresses and opcode and the addresses. So likewise, different instruction here, another one. Opcode means what to do, right? Yeah. Opcode, and then this is actually, these are register addresses. And this I type opcode and two register addresses and memory address. And opcode and the target address, basically memory address. So this is how, so different addresses are there, but you don't want to learn this now. But the problem comes if address is heavy, if address length is too much, it's very difficult to send the instruction. Address එකේ size එක ලොකු වුණොත් අපිට වැඩක් නැහැ. So we have to learn this in there is a chapter for actually assembly language. If you learn assembly language, you have to learn this, but you don't have up to that part here in this examination. No, not assembly language is not there. But if you learn assembly language, you will have these things. So you need to know how the instructions work. Okay, that's it. Right. Okay, so similar to this, the logical address to physical address conversion can happen through MMU. When happen through the MMU, so it can be directly mapping because of the cache, the page cache, or it can go through the page table. Either way, you have to access the physical address. Let me show this in your computer what these addresses are actually. So can you share the screen? Then I can show you what these addresses are.
So you have disabled share.
Can you try now? Right. Please go to Explorer and right click on this PC and select Manage. Then go to this device management. Please. There, let's go to okay, let's go to these. Oh, sorry. So let's type. Let's go to run. Windows key and R key. Windows key and R key. Windows key and R key together will give the run dialog box. Then type MS info 32. MS info information info 32. Press enter. Right, now you get this, and here you can see, just go to the hardware resources and select a subcategory there. Please click on plus sign in the left side. Plus sign in the left side. Hardware resources nearby, there's a plus sign. Now you can select this. Okay, can you select memory, please? Here you can see how the memory address ranges are allocated, right? According to this memory address, how many bits are there in the memory address? Can you tell me how many bits are there in the memory address? You can expand this little. You can expand this. Expand. Click on this bar and expand. So now, by counting the hexadecimal digit in address, can you tell me how many bits are there in an address? How many bits are there in an address? Yes. Count how many hexadecimal digits? 0x means hexa. Then the remaining are the actual digits. So what is, how many digits? Count it and tell me. 8. 8, right? 8 hexa. You have to multiply that by, each hexa will have how many bits? How many binaries? 8. 4.
4.
Is 4. Then altogether, what is the value? How many bits? 32 bit. So your addresses are 32 bit. So if your addresses are 32 bits, you know the range will be 2 to the power 32. This is the maximum address space that you can supply, which means your RAM will be 4 GB. But I hope your RAM is more than 4 GB. What is your RAM? Can you tell me, show me the RAM size by going to the task manager? Is it 4 GB or more than that? Performance. Have to go to the performance section. Here, performance tab. Okay, you can see it's not 4 GB, it's 8 GB, right? It's 8 GB for 7.9 means 8 GB. So means, but your address theoretical range is 4 GB since there are 32-bit addresses. So what should happen here? What do you think? So how it has stored 8 GB then? Is it word addressable or byte addressable? What do you think?
Word addressable.
Yeah, it should be word addressable. Why? If it is byte addressable, the address space is not enough. Right? So that's the thing. Okay, I think you got an idea about how to close this task manager, and also see these addresses are allocated not just for this, it's allocated for DMA, IO, input, outputs. So you can just click on them and see some address spaces are allocated even for these devices. Can you click on IRQ, IO and see this? Okay, it's refreshing, reloading. And you can see some addresses, initial addresses are given to IO, right? Input, output, initial address space is given to that input and output. The first set of direct memory access controller, PCI, you can see system timer. So different addresses to different. You can, like, this is how you should know the addresses, but don't worry, this won't be asked in the examination. Just to know that what these addresses are and how these are represented. Okay, with that, the important topics related to the operating system I have discussed, but I have to discuss about examination question because need to cover some of the sections with the examination paper. So let's quickly go for an examination question and try to understand this part. So I invite you to search with me. Let's search for 2020 A-level ICT paper in English medium. And let's open the MCQ part and also the second part. The first two questions and fourth question, you can see these questions are related to this hardware part. And so 1, 2, and 4. Can you quickly answer 1, 2, and 4 in the MCQ? You can see the screen. It's 1, 2, 4. Just answer. Right, in the A-level paper, you can see like they are not asking much technical stuff, right? A-level paper again, not technical, it's asking the surface, right? So the computer will operate fast when the data that it wants in the cache, hard, magnetic, main, optical, it's in cache, right? It's the first one. So it's a self-explanatory question. I said that the cache is the most fast memory. So that is they are in the processor inside the processor. So it's the fastest memory. The next one is which of the following hardware components? So which of the following hardware components which of the following hardware components will lose data when the power of the computer is asking the same thing, right? It's asking whether which of the following will give you like volatile, which of the following is volatile. So that's the thing it's asking, right? So which is volatile memory? Volatile memory is registers, cache, main, memory. So what do you think?
All are volatile.
Yes, volatile. Registers is SRAM, static random access memory. That is volatile. That will remain. Keep the power only till. So keep the memory only until the power is like there. So it's volatile. Cache memory is inside processor. So it's L1, L2 cache inside the processor, L3 outside the processor, all are volatile. Those are also SRAM, static random access memory. Main memory is a dynamic random access memory. Anyway, all random access memory is there. Static or dynamic, all are volatile. So answer is number 5. So let's move to the number 4 question. The consider the following diagram showing some hardware component connections on the diagram. So it says the CPU, something here, then memory controller, display, DDO controller, keyboard controller, and hard. So bus is basically the transport mechanism where the wires, where the signals. The hardware part, CPU indicated by A, the bar diagram set to register, has set of registers that has the memory translation map. So that is basically we learn. So which has the memory translation map currently running process, which is mapping the virtual, the physical. So it is none other than number, which is number 4 MMU. Number 4 MMU. So we can see. So it's easy. So the actually the paper structure is not like this normally, but in 2020 paper, they have asked much about this operating system part, right? And so then these are binaries we already learned. This, yes, logic gates learn. Block dark, and this part also learn. Yes, logic gate again. 12th question. 12th question. And 13th question. 14th question. 15th question. And yeah, even 16th you can answer because we have learned. 12 to 16, please. 12 to 16. See, so one actually in the examination, 2020 examination, so these are bit technical, but they have not asked 2D. They just ask the surface knowledge whether you have or not. 12 to 16, please. Operating system is another program that runs on the computer that has some special responsibilities, memory management, file management. So you are given some tasks. So some of these, what is another important responsibility of the operating system? Backup. No, there are some utilities to take backup, but it's not very good in backup management. New operating systems are new operating systems are having this backup management part, but still it's not intended to keep the backups. So there are different tools to manage backups better than operating systems. So I'm not going to that answer. Cache memory management, that is also part of memory management. Compiler management, no. Compiler management, sorry, it's process management. Yeah, it's process management. It's clear cut process management. That is answer number 4. 13. When the number of processors start user in a single processor computer increase, what happens to the response time of each process as perceived by user and the memory management related to the operating system, respectively? Okay. Both the response time and the memory management related work increase. Response time increase, right? Processors, when processors are increasing, the response time increase. Yeah, memory management related work is also increased. Yes, that is true. That is true. It will be more overhead, right? Both will be increased. Response time is no. Response time increases. Well, no. Both response time and the memory did no. There is no. Okay, the first one. 14. Which of the following is not a responsibility of operating system? Allocating physical memory to processors. It's a responsibility. Deciding which processor, yes, it's a responsibility. Keeping track of the usage of compiled programs, no. Keeping track which parts of the physical memory are in use, which are, yes, true. Swap-in process. Swap-in means like taking one process and then releasing the other one, swap between the processors. Swap-in is also a responsibility. Swap-in in and swap-out. Swap-in means taking into the processor, and swap-out means taking, like, keep it away from the processor. Swap-in and swap-out. Swap-in, swap-in out is a, so that is how you take new processors and hold existing processors. So the answer is number 3 for 14. Correct. 15. The computer size of a user program could exceed the size of physical memory. Also, the demanded areas of this is page in, right? We explained that is page in. So use of cache, contiguous file allocation table, memory management unit, use of page frames and page tables. 15, answer is 5, right? It's clear cut, because I said that when the size exceeded, it divided into pages. So today's lesson is, I think, very important. If you listen carefully, most of the questions you can answer is in that, right? So you saw that how many questions came from today's lesson. So which of the following statement regarding the compiler's interpreters correct? The compiler transmits entire high-level programs machine code, correct? The compiler does that. Then an interpreter converts high-level program statement to machine code during the program run. Yes. Compile code usually run faster. Yes, that is, compile code is really faster than the other one. So ABC is correct answer C. So your answer is correct. So it is about media, then the modulations, network, bus topology, networking again, testing, software related work, functional, software related, system related, and software project DFT, database, from the database, SQL onto the database back, yes, database part, then database again, and finally this is programming, Python. We have actually learned these lessons, right? You can go through this. All of these are about Python, yeah. Then some HTML. Yes, that's it. And you can see the major lessons that we have discussed now, right? What are the major lessons we discussed? We discussed about the Python lesson and also this programming software engineering lesson. This very important lesson. It can cover 25% of your paper. Now operating system part, so it can also cover considerable part of the paper. We have discussed that, but no question in the second section related to that in this time. But other days there was some question. And programming part, there are some questions. So next three important topics: networking, databases, and web. So those are the next three important sections: databases, web, and database, web, and networking. So those are the next three important sessions. Once you learn all these things, very easy to cover the syllabus and answer the questions and get marks. So that is our plan. So anyway, so there will be small change in the class time. Maybe there are some students reporting that they have some other classes, won't be able to come on this time. I'll let you know by next week what's the exact time that we can conduct the class. So I'm stopping from here. We'll go to the new lesson, which is database. I think preferably database lesson is, so it's a good lesson that we can start and cover quickly. Next, I'll go to the networking lesson, which is quite hard. Again, having some technical stuff. And finally to the next major one, which is HTML part. Actually, I have already covered that in the evening class. So if you have not covered, so I'll take a list of the lessons that I have not covered and then go through, because some of the lessons I have covered with the evening class. That's the thing. Anyway, I'll discuss with you and others also and come to a conclusion which lesson we will be doing. Then I'll stop from here. Good night.
Good night, sir. Thank you.